Okay, so welcome to the lecture 5 of this lecture series. Last time we have seen theory of colocalization, the correlation, the causality, association, and then we have seen different correlation coefficients, followed by normalization techniques and the chi-square test. Okay, so today we're going to do the multiparametric analysis, where we will see the multiple linear regression, logistic regression, and then we will see the area under ROC as the evaluation criteria. Okay, so what is a multiparametric analysis? When you say multiparametric, you will understand that, so multi means like many, right? So far we have seen only single feature for particular samples, and we have seen different tests, for example t-test and the z-test and all other tests, like where we just compare the p-value between the two variables or two groups when they have only one feature, but not necessarily all the time you will have this one feature. One sample can have many features, and then how to build a model based on that and then evaluate its performance or classification between these two groups. Okay, so for that we have to understand what is a multiparametric modeling or multiparametric analysis. So we have also seen last time that the correlation is a statistical relationship. It is called as a covariation between the two random variables, and the way you quantify that variation is by the correlation coefficients, right? And we have seen that example with the GFP and M-cherry last time. So the relation can be positive, which is like a GFP increases at M-cherry increases, then the GFP decreases at M-cherry increases, and there can be no relationship. Yeah. So you can quantify this using the Pearson's correlation coefficients. And we have seen very importantly that the correlation is not a causation. So in order to identify if there is a causation or not, you have to do a randomized control experiment, or randomized control trials, or systematic review, or whatever the standard experiment, right, with the control environment. So we have also seen that during this Pearson's correlation coefficient, you have a data points. You try to fit lines, right, which passes through these lines and minimizes the error for this every individual points to that line, right? So we choose that line which minimizes the error, which has the minimum error to the fitting to that line. Okay, and based on that line we can identify the relationships such as the GFP is equal to A plus B times M-cherry. So A is called as an intercept, B is called as a regression coefficient, yeah, and depending on what is the sign of B, that is positive, then it's a positive correlation. If it is B is negative, then it's a negative correlation. Okay, and based on this one, we have also computed that the Pearson's correlation can go from -1 to +1, depending on how the relationship is between these two variables. Okay, so this is all about the correlation, right? So how the correlation is different than the regression. So one thing is very important, even though this plot look like what we have used during the correlation, but there is one important point that differs from this correlation, that is the independent variable and dependent variable. So the y-axis we will always have a dependent variable, and x-axis will always have an independent variable. So independent variable in the literature can be called as basically it's a variation that causes the relationship, the variable that causes the relationship. Okay, and sometimes it is called as a predictor variable, regressor, control variable, manipulated variable, explanatory variable, exposure variable, risk factor, feature, input variable. And the dependent variable is called as the variable that explains the relationship. Okay, sometimes it's called as explained variable and response variable. It's also called as output variable also. So how regression is different than the correlation? So we have seen that in the correlation we can have this line. What regression does is that it predicts the future input. Yeah, I mean it predicts the output based on the input variable. So how does it do that? So once I have a line here, if I have a point xi, which is my input variable, in future I can draw a vertical line and then find the y-intercept on that particular position, and that would be the predicted output variable. Okay, so this is the one advantage that one can have a regression over the correlation. Also, with a multiple linear regression analysis, which we're going to see it, we can assess whether or not there is a importance of any input variable, and if there is any relationship between the input variable to the output variable, and how many input variables are significant, or how many of them are correlated and they carry the same information. That all kind of analysis we can do that using regression. So then there is something called as a multiple linear regression. So when there is only one input variable, that is called as a linear regression. When there are more than one input variable, such as in this case we have a GFP as output, but mcherry, in addition to mcherry we have the Texas red as a input variable, then it is called as a multiple linear regression. And in this case we try to fit a plane, right? We try to find a plane which goes through all these data points and minimizes the error to that particular plane, right? The fitting error. And then accordingly we can find an equation for that particular plane, which is equal to y is equal to beta 0 plus beta 1 times x1, beta 2 times x2, where x1, x2 is the mcherry and Texas red respectively. Yeah, where the beta 0 is just the intercept that we have seen in last slide. So to just give an example, this can be applicable to any scenario where there can be more than one input variable, such as if I do a high content screening experiment, then where the output variable is a foci count from the GFP channel, that is my output variable, and the input variable is the integrated nuclear intensity from DAPI, shape of the DAPI, Texas red channel foci count, Texas red channel foci intensity per nuclei, and n number of input features. So if I have a such scenario, then I can build a model on this foci count for the GFP channel. That is called as a multiple linear regression modeling. Yeah? And the equation for that particular model would be the same. And as you can see that if there is n number of input variable, then the beta would be the n numbers, right? So number of beta would be that particular numbers as equal to the input variables. So let's take an example for this one. So I have taken this example from the MathWorks source. So as you can see here, there are different variables that determines a particular person's information, such as the surname, the gender, the age, the weight, and the whether or not they smoke, their systolic and diastolic blood pressure. Yeah. So what I have to do now is I'm trying to build a model based on this input variable. So this is my input variable, right? Independent variable, I can say, and I want to build a model for determining the systolic blood pressure. So here my output variable would be systolic blood pressure. So if you have such scenario in your experiment, you can apply the regression. Yeah? The way you do it in MATLAB is very simple. You just, so it's a fit LM, that is the fit linear modeling, that is a function in MATLAB. And this is you just have to say that what is your response variable. So response variable would be your blood pressure, and the predictor variable would be all your input variable. These are just the terminology used by MATLAB. Yeah? And then you have to give what is that particular, and this hospital is nothing but the name of this table in MATLAB. This is how you call the table in MATLAB. Yeah? Okay. And what it gives you is basically this MDL. MDL contains the model, that the fitted hyperplane. Yeah. Okay. Most important is how to interpret the result. So I'm not going to go into detail if how the hyperplane is fitted. That's basically a maximum likelihood estimation and all mathematical equations and all these things. So what is important as a biologist is to interpret the result of logistic or the multiple linear regressions. Yeah. So for this example, this will be the output. No matter if you use SPSS, SAS, or whatever the statistical software, you're always going to find the output like this. Yeah. With the different orders and all, but the features would be the same. Yeah. So first line indicates that the blood pressure is my output variable on which the model was built. Using the input variable, the gender, age, weight, and this whether or not they smoke or not. Yeah, this is what it tells you. Then there is an estimated coefficient. So you see that there are 4 columns, and that 4 columns is for all every input variable, including the intercept. So forget about the intercept. That is just for the regularizing the model, but these are very important. So these are all the input variables. Estimate is nothing but the beta basically. Yeah. So you can see that the equation would be for this logistic model is a blood pressure equal to beta 0 plus beta 1 times the gender plus beta 2 times the age, beta 3 times weight, and beta 4 times smoking habit. Yeah. And this number is nothing but that beta value. Yeah. What is the standard error? We have seen in lecture 1, right? What is the standard error? Standard error is the standard deviation in a sampling distribution. So just at this moment, this is not important to understand basically standard error in a t-stat. What is important for you to actually understand the p-value, because p-value was computed based on the SE and estimate and the t-stat. So what it does is actually, so you estimate, the table gives you this output variables, the beta 0, beta 1, the standard error for that, and if you divide estimate by standard error, you get the t-stat, that is the t-statistics we have seen in lecture 3, in t-distribution, how to compute the t-statistics and all. So once you get this t-stat, using the t-distribution table, you can find the probability of rejecting null hypothesis. Yeah. So with this, you can say, just by knowing the p-value, the smoker has got a significant p-value, meaning that we can reject the null hypothesis that there is no correlation, or what you call regression, or the significance of smoker is null. So what it means is that the smoker, whether or not you smoke or not, significantly depends or decides the blood pressure. This is what it means. Yeah? Or basically the contribution of this input variable is significantly higher as compared to others in order deciding the fate of the blood pressure. This is one interpretation, right? Then another output variable would be, the feature would be the number of observations. So there are 100. The error degree of freedom is 95. We have seen what is the degree of freedom, right? Degree of freedom is nothing but the number of sample size minus 1. And in this case, it is 100. So 100 minus 1 is 99. But in case of multiple linear regression, you also have to take care of how many input variables you have. So it's a 99 minus 4, that would be 95. Okay? Root mean squarer, it is just the value which will tell you how well the model is fitted, right? What is the error, the mean error of all the data points to the hyperplane. This is not important. What is important is this R square. So R square value, last time we have seen during the correlation that the R square is nothing but the coefficient of determination, and the ideal value for coefficient of determination is 1, and here it is 0.5. It means that your model is not well fitted to the data point. So there is a lot of errors. This is what it means. So you should not believe too much in predicting this the value using this model. Okay, so we should not use this model in a very accurate manner, because the R square is very low, right? So the model is not best fitted to the data set. The adjusted R square, you might have seen this in many during ANOVA also and during correlation also. So what does it mean actually? If the degree of freedom, there is a relationship between the degree of freedom and the R squared value. So if the degree of freedom decreases, R square increases, no matter how many significant features you have it. Yeah, and we have seen the degree of freedom decreases as the input feature increases. So in my model, if I put many number of input features, no matter how the input features, whether or not they are significant or not, the R square would increase. And that is a bit deceptive, right? Because then they would say it is always good to add many number of features as much as possible, right? Which is not true, because it doesn't matter how many features you add. If they are non-significant or nonsense, your model should not improve the accuracy. Yeah. So in order to control this criteria, in order to control this deceptiveness, one can use the adjusted R square, which will take care of whether or not the features, that input features, are correlated or not, or they significantly contribute to the model or not. Yeah. So it will take care of the degree of freedom and the R square things. That's why it's so adjusted R square will always be lower than the R square value. So always report this one. That's important. Then the fourth one is the F statistics versus the constant model. This value will give you some p-value. This particular result will give you some p-value. And what it means is, it is nothing but the output of ANOVA. We have seen that analysis of variance, right? In analysis of variance, we have seen that if the p-value is significantly higher, meaning that we can reject the null hypothesis that none of them or all of them comes from the same distribution, or they do not have any variation. So what it means is that at least one of this input feature contributes significantly to the model output. This is what it means. Yeah. Okay, but I think this is not important because this p-value itself will tell you that this input feature is significantly contributing to the model. Yeah. Okay. Now, the multiple linear regression. Let's take an example, another example, where my output variable is now weight. For example, the response variable is weight, and then based on input variable, I want to predict the weight based on the gender, the age, and the blood pressure. Yeah. So if I do that, again I can have the same output, well, the similar output, and the input variable, and all the information pertaining to particular input variables. Yeah. Likewise. So here also you can see that the age does play important role. The gender. So gender is significantly contributing to the model as compared to the others. Well, others are non-significant, right? Number of observation 100 as same as before. Degree of freedom is 96. You see now it's 96 because it's 3 only, right? 3 input feature and the 100. So 100 minus 1 minus 3, that would be 96. R square value is 89, so 0.89. So that has improved from the beginning, from the previous example, because just by switching the input and output variable, see the difference. The adjusted R square is 0.89 still, and ANOVA is significant, meaning that there is at least one variable which significantly contributes to the model. Okay, but this example will tell you how the information, the output information would change, right? If you just switch from one input variable to another output variable, yeah. But that switching has to be meaningful, yeah. Okay. There is also a possibility that you can that the output model or output variable is not only dependent on input variable, but the combination of input variables. And that is called as interactions. And it is possible in MATLAB to have this interaction to play between the input variables. Yeah? And that you can do it just by writing these interactions, as you can see to right. So what it tells you that your output variable is dependent on the combination of every possible input variables. Yeah? Every possible combination between the input variables. And the output you will see depending on how many combinations you have. You can see that the original one, that is 3, like the age, the gender, smoking, and then all possible combinations. So it becomes 6 now. That's why the degree of freedom has reduced from 96 to 93. And R square is 0.89. And if you see that the p-value, it's the same as before, that the being male is significantly contributing to the weight prediction. But also if you closely look at this particular one, that the gender and the age is also significantly higher. Well, if you relax a little bit level of significance, not 0.05, but if you just relax a little bit, then you might see there is a significantly relationship between the gender and the age to the weight. Okay. So we have seen this example where the R square was very low. Yeah, that's 0.5. Then if you have such situation and you cannot switch over and you are really interested in predicting the blood pressure based on this 4 input feature, how do you improvise this model? Because you cannot use this model for predicting the future input variables, right? How to improvise this? The one way to improvise is to use this plot. Now I'm not going to go into detail how to get this plot, but there is a possibility in MATLAB to get, once you have the model, you can build a scatter plot where the x-axis is the residual and the y-axis is probability, where you will find those data points which are a bit offset to the linear line, to these linear correlations, right? So the points which are fall away from this line can be considered as outliers. So they are not fitting and they are basically contributing noise to the model. But again, I'm telling you, this is very important, that you should not just directly use this approach and just get rid of this outlier, but you should investigate and go back and see if this is really an outlier, because sometimes this can be a very significant information. You cannot just completely ignore that. Yeah. So be careful about that. But there is a possibility of getting rid of this outlier, and once you remove this outlier by I say this exclude outliers and build a model again, then I can get this particular the model variables, and you see that the R square has improvised from 0.5 to 0.65, and the adjusted R square was improvised from 0.48 to 0.62. Yeah. So this is how you improvise this model, and then this model may be useful in predicting the future output, yeah, based on the input variable. Okay. So this is an example. So if I use this model in predicting, let's say this is just the 10th row of that particular table that I showed you, then it predicted the systolic blood pressure was 118. But if you use this model in predicting the output would be 121. So you see that it is very important, because it might mislead you, because here it was underestimated the actual systolic blood pressure. Yeah. So this is very important to use a proper and the optimized model. And this particular process is called as the parameter tuning, or it's also called as reducing the training error in all the different domain. Yeah. Okay. So generalized linear model. Okay. So we have seen so far that we have an independent variable in x-axis, and y-axis we have dependent variables, output variable, input variable. But we have seen the output variable is a continuous variable so far. But not necessarily that all the time we have this output variable to be continuous. We might have such situation. We can have either the count data like 1, 0, 2, 1, 2, 3, 4, 5, 6, nothing in between, right? Or we can have a binary data like a 0, 1, yes and no kind of category. Or we may have the categorical data, like for example, red, green, blue, and violet, and all this kind of a color category. Or we may have the ordinal data, for example, minimum, maximum, median, all kind of the ordinal data. There is order in the data variable. In such cases, we cannot use actually the linear regression. And we are going to use now, because of the time limitation, we won't be able to cover all these models, but there is one particular generalized linear model that is called a logistic regression and a probability regression when the output is a binary. Because in most of the time, we have this experiment of whether or not we basically compare the two groups, right? The yes and no, and the positive and negative control, and likewise. So the logistic regression is extensively used as far as the generalized linear modeling is concerned, as compared to other modelings. Okay, so we're gonna spend more time on understanding logistic regression now. Okay, so why generalized linear model is needed, right? If you see that, just take a same example where my input variables are the gender, age, weight, but instead of blood pressure now, which is a continuous variable, now my output variable is smoker, right? Whether or not I want to predict the smoking habit based on these input variables. So how do I do that? So if I use the linear modeling, or the linear regression, yeah, the multiple linear regression, then I cannot use this, because the output variable is not continuous. So in that case, we have to, this is one example, right? This is the one way of interpreting the limitation of linear modeling or linear regression. But let's take another example. I have an input variable. For the simplicity, I just have one input variable, and the output variable is smoking. And if I try to plot this particular data on the scatter plot, so my x-axis is weight, y-axis is smoking, and if I just plot, I can have this situation. Now, if I wanted to use a linear regression, I will try to fit a line, right? This is always a procedure in order to find a linear regression. So if I try to fit a line, it is not possible to fit a line, you see? Because there can be any line which can pass through this two particular, and also it is not good because none of them actually fitting to the line, right? They are far away from that particular line. So there is no best fit regression line in such cases. So we need something else, and that is something else is called as a logistic regression. So what it does is that you have an input variable, There is a logistic regression model which gives you an output of the output variable, and our output variable is here being a smoker. Yeah. So the name logistic regression has come from the mathematical operation called as a logit. And what is logit? Logit of smoker, and this model can be written as the logit of smoker is equal to beta 0 plus beta 1 times weight, which is the input variable. Yeah? But first we have to understand what is the logit. The logit is nothing but the natural logarithm of the odds of smoker, the output variable here. And to understand what is the logistic regression, one need to understand what is the odds of smoker. Yeah. So for that we will understand in next slide what is the odds ratio. And we have seen actually in the last lecture, but I will just repeat this again. So to understand the odds ratio, in lecture 4 we have taken this example where there are 193 patients which was given the drug A, and 119 given the drug B. Yeah, and 153 out of them for the drug A was responded to the drug A, and the 50 of the drug B trial was responded to drug B. So so once you have this information in the table, the contingency table, what I can extract the information is that 153 divided by 193, which is the 0.79, is the probability of responding to drug A. Yeah. Similarly, not responding to drug A would be 40 divided by 193, and similarly for drug B also. Yeah. Furthermore, we can use this information in order to say that the odds of responding in drug A trial is nothing but the odds of responding in drug A divided by odds of not responding in drug A. Yeah. I wouldn't say odds basically, it's just a probability. It's a probability of responding in drug A divided by probability of not responding in drug A. That is the odds of responding in drug A trial. Similarly for drug B trial, the same thing. And the odds ratio is nothing but the ratio of these two guys here. So the odds in A divided by odds in B, which is nothing but the 5.30. What it means? It means that the odds of responding in drug A is 5.3 times more as compared to odds in responding in drug B. Yeah, good. So coming back to this, the previous slide, that this is a logistic regression, and the log of odds of smoker. So we have understood that the odds of smoker is nothing but the probability of smoker divided by the probability of not being smoker. That is 1 minus probability of being smoker, right? And I can write that as in the right hand side likewise, and then just by linear algebra, just changing the variables right hand side to left hand side, I can get the probability of being smoker. So the probability of being smoker is equal to 1 over 1 plus the exponential of my right hand side, which is the minus beta 0 minus beta 1 times the weight, which is the input variable. Yeah, okay. So once I know the weight, right, then I can compute the probability of being smoking. And let's see how it behaves in a scatter plot, right? Because that will be more intuitive, right? So same example, I have an input variable, output variable. If I put in a linear way, right, if I try to fit a linear line, just a linear model, it is not possible because the line is not fitted to that particular data set. But if you use a logistic regression, your input variable is the same, but the output variable is no more the smoker, but it's the probability of being smoker, which is a non-linear, as we have seen, it's exponential, right? And if you closely see this curve, is a sigmoid. So what it tells you that if you are in an extreme part here, the right hand side, the probability of being smoking is towards 1, and if you are in an extreme left hand side, then the probability is close to 0. And if you are in between, then there is a probability between 0 and 1. Probability is always between 0 and 1. But this gives you a kind of a flexibility in getting the output value, which may be in between this 0 and 1, unlike this one. Yeah, that is the beauty of logistic regression. Okay, and in MATLAB, how can you do that? You just say glm fit, that is a function of MATLAB. You just put the input variable, the output variable as a smoker, and you say binomial. So I don't think so it is important for you to understand this, but the logistic regression is nothing but basically it's a Bernoulli's distribution, and Bernoulli's distribution is a spatial condition or spatial case of binomial distribution. So that's why it is closely related. So that's why you have to put in MATLAB and say that it's a binomial, right? So that's why, so once you do that, you get this beta. Beta will have this beta 0, which is the intercept, and beta 1 because it is only beta 1 because it's just there is only one input feature, right? And then you can use this glmval function in order to evaluate this model in order to predict the output of this weight variable, yeah, using the logit as a keyword. So you get the probability of being smoker based on any future weight feature here. Good. So let's take a practical example of this one. So I have taken this example for the high content screening, because especially for CPR we do a lot of high content screening, and we have been using logistic regression a lot, especially for the Claudia's group. So typically, if you do high content screening, you have this plate layout, 96 well plate, where the first column and the last column we have this positive control shown in green, negative control in red, in a two extrema, right? Normally we have seen in the age biasing, right? This should not be a way, it should randomly placed everywhere, but just for the simplicity, let's take this as an example where you have the positive and negative control and positive and negative control, and then in between you have all the siRNA with respect to different genes that you are targeting on, or you are interested to know the phenotypes. Yeah. Okay. So what you do in as far as microscopy is concerned, you acquire images from different wells or different field from this particular conditions, the positive and negative control. So here this is just an example. I'm just taking a DAPI and RFP. Okay. What you do is you extract features from DAPI and RFP likewise. So you can have area, position, the circularity factor, the intensity, 53 BP1 foci count, all kind of features that you extract from this. These are the cellular level information, okay, by the way. So once you have this extracted this feature, you can tell that feature, so now it is shown as a P, yeah, P1 to P10, and you can say that the log of the probability of cell being positive control divided by probability of being cell negative control, because you understand this is the probability of cell being positive control divided by 1 minus probability of being positive control. That is nothing but the probability of being negative control, because we have a binary output, right? The positive control and negative control. These are the like what we have seen in the smoking, whether or not you smoke, yes or no. Likewise, we have this positive control and negative control. So I try to fit a model on the output variable, which is a binary, which is the probability of being positive control, that is my positive class, equal to the beta 0 plus beta 1 times all individual features up until beta 10, yeah? Okay, so if I rearrange this, then I get this probability of cell being positive control can be written as this equation. And what I have to do is I have to just extract these features from all siRNAs, plug into this equation, and get the probability of every cell, and then aggregate all the cells from all the fields from all the wells for that particular siRNA to get the one probability value. That is called as a voting criteria, okay? So what you do is you extract all these features from every individual siRNAs likewise. Then you, using this equation, you get the probability for every siRNAs here. And then you put you place a heat map, you quantify the heat map for the probabilities for all siRNAs likewise here. So depending on how big is the probability or how close that probability towards the positive control, you can categorize different siRNA and thereby different genes which are responsible or which has a phenotype close to the positive control as compared to the negative control, yeah? And that can be meaningful in order to compare between the different groups, different conditions. So this is one application of logistic regression, high content screening, yeah? Okay. So let's, then another advantage of using logistic regression is that one can have the odds ratio to be computed, can be computed from the logistic regression. So same example of the hospital data, you have an input variable, the age and weight, and the smoking as output variable. But you can also have the systolic and diastolic pressure here. This is just an example. So if I do that likewise here in that we have seen in the MATLAB, I get the beta 0, beta 1, beta 2, beta 3 and beta 4. Once I have got this value from the GLM fit, the probability of cell being, this is just an equation, right? The odds ratio can be computed as the exponential of the beta. That is very straightforward. You don't have to calculate and you don't have to compute this contingency table and all these things. This is the really beautiful advantage of being of using the logistic regression. So you just compute the exponential of the beta value that you get from this model, and whatever that model will give you, that odds ratio will be 0.99 for this age, beta 1.0 for the weight, and likewise for the systolic pressure now. So, but what it means actually, so we have seen in the previous slides that the odds ratio 1 means that there is no change from A to B during this drug trial, right? If it is more than 1 means that the numerator has more odds than as compared to the denominator, and if it is less than 1, it's inverse, right? So let's interpret the result that we got from this data. That is so 0.99. What it means is that 1 year increase in age decreases the odds of smoker by 1%, because our output value is variable is smoking or smoker. So an input variable for the age. So 1 year increase in the age decreases the odds smoker by 1%. Similarly for this one, it's a 1.0, means that 1 kg increase in weight does not change the odds ratio, because there is no odds ratio. Odds ratio is 1, meaning that doesn't change. 1.03 meaning that 1 millimeter of mercury increases in systolic blood pressure increases the odds of smoker by 3%. Yeah, this is what it means. And similarly for the diastolic pressure. Okay, so this is how you interpret and you calculate the odds ratio from logistic regression, and this is how you interpret the result with respect to the input variable. Yeah. Okay, so in the regression we have seen linear regression, where you just have a one input variable and output variable is continuous. If you have more than one input variable, that is called as a multiple linear regression, and still output has to be continuous. But if you do not have a continuous output, but if you have a various different distributions or the type of the output variable, like the count or the ordinal data or the categorical data or the binary data, then you can that modeling is called as a generalized linear models. And we have seen one example where the output is a binary, that is called as the logistic regression. There is also there is something called as a nonlinear regression modeling, right? So once you have tried everything and maybe you are not able to find a proper hyperplane of yours, or still your R square value is still low and you're not finding a convergence to your input data variables, then one should think of going for nonlinear regression models. Okay, so some examples like the Huygens-Watson model, and in MATLAB you can actually try different nonlinear modeling, right, using this tool which is shown in the slide. But we don't have time to do that now, and it is very unlikely that you're going to use it. And I have not seen, to be honest, in any biological paper using nonlinear regression modeling. Yeah, it's a bit difficult to explain the outcome and interpret the outcomes because we might you are more tend to have overtraining, right? Because it's when there is a nonlinearity, you can always try to overtrain your model, and your prediction may not be reliable, right? Okay. So last time we have seen this chart where there are different purposes of your hypothesis and the nature of your sample. Based on that, you have a different tests, right? So especially for this particular purpose, which is the difference of means. So if you want to compare between the two different groups using their means, then we use either t-test or z-test. In t-test, we use a paired or unpaired test. But if you have the similar situation, there is also one more non-parametric evaluation test that is called as a area under receiver operative characteristics, called something simply called as AUC, or it's called as AZ with suffix Z. It is basically similar to the Wilcoxon-Mann-Whitney test, so it's also non-parametric, but I would say it is more robust and it is more, what do you call, it is more, it's more intuitive, right? It's more intuitive, and we will see why it is more intuitive. So let's see that. So ROC curves is the graphical plot that illustrate the performance of binary classifier. So it is mostly useful for when you have a two-class classification, yeah, where the outcomes are there and you want to compare between the two classes, the outcome of two classes. And it is non-parametric, as I said before. So what it means? So in order to understand ROC, one need to understand this contingency table when you have a two-category output, right? So you have a true condition, so that the condition could be positive and negative. This is a two-class classification, and this is a true condition, while the predicted condition can be also the two types, positive and negative. So if you predict something positive, which is actually a positive, that is called as a true positive. And if you predict something negative, which is actually negative, that is called as a true negative. And if you do a mistake in, so if you predict that as a negative, but actually it is positive, that is called as a false negative. And similarly, it is called as a false positive. And whether or not they are false positive or false negative, they are called as a type 1 error and type 2 error. We have seen in lecture 2 what is type 1 error, type 2 error, and how type 2 error decides the power of your study and all those things. So, okay, but once you have this chart or once you have this table, one can directly see what is the prevalence. So prevalence is nothing but all the positive conditions here, in this case, divided by the total population. Total population from negative and positive. That's the prevalence. And the prevalence you might see in all the literature, that the prevalence of cholera during this, in this particular population, in this particular study, was that one for that particular year, right? So that's prevalence basically. One can compute the accuracy, which is nothing but the true positive plus true negative divided by total population. That's the accuracy. Okay. Now if you just only focus on the row, the two rows, then one can compute the true positive rate, TPR. It's also called as sensitive, which is nothing but the true positive divided by total positives in this row. And similarly, you can have a true negative rate, which is the specificity, which is the true negative divided by all negative conditions. And then you can also find the false negative rate, which is nothing but the false negative divided by total positive conditions. That's called as a false negative rate. Similarly, you have a false positive rate, also called as a fallout rate. Okay. If you now focus on the column wise, then you can have the positive predictive value, which is nothing but the true positive divided by total positive outcome by the test. And similarly, you have a negative predictive value, true positive divided by true negative divided by all the negative tests. And you have a false omission rate and the false discovery rate. The false discovery rate we will use mostly in the proteomics, right? Okay, so once I know this, I can also extract one more information that is called as the positive likelihood ratio, which is nothing but the true positive rate divided by false positive rate. True positive, false positive rate. And you can also have the negative likelihood ratio, which is nothing but the false negative rate divided by true negative rate. And once you have that, you can compute the ratio of that, the odds ratio. So the diagnostic odds ratio is nothing but the LR plus divided by LR minus. So if the diagnostic odds ratio is 1, meaning that the test, the predictive test is equally likely to find the positive and negative conditions. This is very important. And if it is more than 1, means that it is more tuned to find the positive likelihood as compared to the negative likelihood. Yeah. So the odds of finding positive cases is more as compared to the odds of finding negative cases. This is what it means. Okay. And most of the people get confused with the sensitivity and specificity. Sensitivity is very important when you are really interested in finding true positives. So one example for the sensitivity is that if you have a machine in the airport, right, the security machine, so the sensitivity has to be higher, because there important is to find the true positive. So the person with a suspicious object in their pocket, the machine should find that person. And it is okay if it finds the false positives. That is okay, that's fine. Well, in case of specificity, the example would be the histopathology test. Like, for example, if you have a cancer and if the machine detects a cancer for a woman who actually do not have a cancer, she might have to go through the histopathology, and that is a very painful procedure. So you want to avoid that. So in that case, you need more specificity for that particular instrument. So there are two compromises between this. So it depends on what kind of application you are tuning to. Okay. So how does it relate to the receiver operative curve? So if you see that this is my example, I have a group 1. I have just 8 samples, group 1 and group 2. My objective is to compare whether or not the group 1 is different, significantly different than group 2. Okay. One straight away is that I just compute I see with using this Anderson-Darling test whether or not they are coming from the normal distribution, and then I'll just straight away use the t-test, right? If not, I will use the Wilcoxon-Mann-Whitney non-parametric test. But also you can use this receiver operative characteristics curve. So how does it work? So in the threshold, there is something called as a threshold, right? In threshold, you can have all the possibility from minimum to maximum from all this from these two groups. So what is the minimum value? That's a 10, and maximal is 56 from these two groups. And you find all possible true positives and false positive for every threshold, likewise, as we have seen. So in the group 1, this is the one curve, group 2, this is another curve, and for every threshold, which is this vertical line, right? This vertical line gives you the threshold. So for every threshold, you will have this contingency table, as we have seen in the previous slide. So true positive, false negative, and true negative. And based on that one, you plot a scatter plot where the x-axis would be false positive and y-axis is your true positive. And you keep on plotting this point for every possible threshold. So you can have plot like this one where every blue point here has come from this threshold. Yeah? And then you just join this points to make a curve. So how to interpret this basically? So to interpret is that the diagonal line will tell you the difference by chance. So the area under this, the area below this line is just the area which would be 0.5 because the entire area is 1, right? The total area is 1. So the half of the area is just 0.5. And if you get anything on this line, then you can say that this difference between the group 1 and group 2 is just by chance. But now in our case, we get something bigger than this area. So this area under this curve is called as the area under ROC, because this is a ROC curve and this is called as the area under ROC. And if the area is more than 0.5 and the bigger is this area, the more meaningful difference is there between the group 1 and group 2. This is what it means basically. And the reason why I have covered in logistic regression, because in logistic regression normally the output variable is a binary variable, right? So mostly, I wouldn't say always, but most of the time, the output of logistic regression is evaluated based on the area under ROC curves, okay? And apart from that, mostly in the medical imaging, I have not seen in the biology people have been using this evaluation criteria, but this is the most robust criteria because you can go through all possible thresholds, right? So there is no assumption of the distribution of the input groups. So it's very useful. So thank you so much. So next time we will cover the guidelines for reporting statistics in publications. So mostly I will take an example from Nature publications and the New England Journal of Medicine, right? All how to report and how to answer and how to make sure that the questions that they have asked is already been utilized or has already been answered in your the manuscript. Okay. So thank you so much. Is there any question for us? Yes. Go ahead.